This is a shorter chapter as you can see through here. Chapter 11 deals with two main topics, tests for goodness of fit and tests using contingency tables. So we're still doing hypothesis testing as we go through this. The Chapter 11 objectives. Test the distribution for goodness of fit using the chi-squared. Test two variables for independence using chi-squared. And test proportions for homogeneity using chi-squared. So you'll notice we're using chi-squared on all these values here. So as we go through these tests, you want to make sure you know what table to use, what equations to use, and it won't be too bad from there. So let's start as we go through here. Let's see if I can get my slide working here. The chi-square statistic can be used to see whether a frequency distribution fits a specific pattern. We've dealt with chi-square before. This was referred to as the chi-squared goodness of fit. Here's the test. It says formula for the test for goodness of fit. Chi-squared is equal to the sum of O minus E squared over E squared. E. O is the observed value, E is the expected value. Degrees of freedom is always the number of categories minus 1. The assumptions of the goodness of fit test. The data obtained from a random sample and the expected frequency for each category must be 5 or more. That's an important part right there to remember, is that the expected value must be 5 or more. So chapter 11, other chi-square tests. Let's try a problem. A market analyst wished to see whether consumers have any preference among 5 flavors of new fruit soda. A sample of 100 people provided the following data. Is there enough evidence to reject the claim that there is no preference in the selection of fruit flavored sodas? Use alpha 0.05. So the first thing we're going to do here is state the hypothesis. And these are little different hypotheses as we go through. Our hypotheses here are going to be consumers show no preference, consumers show a preference. The claim says consumers show no preference. We're going to find our critical value. Now it says degrees of freedom is 4 and alpha is 0.05. So our critical value, it says here, is 9.488. So now how do we find the critical value? Well, if you go to your back of your book, and I think this is in your charts too, but I'm not positive. I'm going to get to the right table so I know which table I'm working with. Chi-squared is table G. We're working with 0.05. And we got 4 degrees of freedom. 0.05, 4 degrees of freedom. We have 9.488 as our critical value. Now, notice here our expected value. We had 100 different people. If it's equally flavored on all these values, that means 20 people should have each flavor. So that's the expected value. Now what we're going to do next is compute our test value. Now our test value, I want to show you through here. What we did on our test value is take our expected 32 minus our observed minus our expected squared over our expected. 28 minus 20 over 20, 16 minus 20 over 20, 14 minus 20 squared over 20, and add them up, and we got our test value of 18. Now we're going to make our decision. So I'm just going to see if I can delete that. Oh, that's a mess. Hang on. There we go. This decision is to reject the null hypothesis since 18 is greater than 9.488. Since 18 is way over here, there is enough evidence to reject the claim that consumers show no preference. In other words, there is a favorite flavor that they like to work with as they go through. Now, one of the things about this chapter you'll notice is that a lot of the tests are kind of set up the same way. So let's try another one. The Russell Reynolds Association surveyed retired survey executives who had returned to work. They found that after returning to work, I'll let you read the whole thing here. Okay? So observed. This is what was observed. New company, 120. Self-employed, 76. 17 owned company. Now what we have here is our null hypotheses, and I wanted to point out what they did here. This is a very long null hypothesis. The retired executives who return to work are distributed as follows. 38% are employed by another organization, 32 are self-employed, 23 are either freelancing or consulting, and 7% have formed their own company's claim. The distribution is not the same as stated. So, I mean, we surveyed 300 people. So if we went along here, 38% of 300 is 114, should be here. 32 should be 96. 23%, 21. Now our critical value on here, if we looked at our critical value, degrees of freedom, there's 4 groups, minus 1 is 3, alpha 0.10, 0.103, we got 6.251 is our critical value. Now if we test our test value, oops, wrong button. Here's our test value. O minus E, 122 minus 114 squared over 114, 85 minus 96 squared over 96, 76 minus 69 squared over 69, so on. We get our test value of 3.2939. So what do you think? The test value, you notice here, is smaller than our critical value, so therefore our decision, if you look at the chart here, notice that our test value is here, critical value is there. So our decision is there is not enough evidence to reject the claim. It can be concluded that the percentages are not significantly different than those given in a null hypothesis. So there is not much difference between them. Here's another example. A researcher read that a firearm relates deaths for people aged 1 to 18 were distributed as follows. 74% were accidental, 16% were homicidal, 10% were suicides. In her district, there were 68 accidental deaths, 27 homicides, and 5 suicides during the past year. At alpha 0.10, test to claim that the percentages are equal. So if we look at the next value here, I didn't get the whole, I'm just going to go here. Here's our hypotheses. The deaths due to firearms at age 18 are distributed as follows: 74%, 16%, and 10%. Distribution not stated as same. Now there was 100 people here, so 100 people at these percentages means there should be 74 expected, 16 homicide, and 10 suicides. So we have to find our critical value now. 3 categories minus 1 is 2. Alpha 0.1, it's 4.605 is our critical value. Now our test value, 68 minus 74 squared divided by 74, 27 minus 16 squared divided by 16, 5 minus 10. So you keep finding the differences. Is the differences high enough? Notice on this one, our test value was 10.59. Our critical value is 4.605. So if we're testing here, wrong thing, our critical value is inside there. So there is enough evidence to reject the claim that the distribution is 74, 16, and 10. So therefore it's not 74. It's enough evidence to reject that claim.